This video is the second in a series to understand and deal with controversies. In science, the goal is always the truth. The path to get there must always be rational and logical. That being said, our analysis is also suitable for nearly any topic, so long as the goal is truth and logic. Affairs of the heart are likely exceptions. To begin, let's first look at how controversies get started. Most often, a topic becomes controversial when two sides offer seemingly logical arguments, but arrive at opposite or incompatible conclusions. This usually occurs when one or both sides have introduced logical fallacies into their arguments. Although the arguments may appear sound, the fallacies allow false or invalid conclusions to be drawn, and this leads to controversy. Therefore, it is important for us to be able to identify some of the most common logical fallacies. The first fallacy on our list is the converse error. It has a symbolic form like this. We read the left side as the statement, if P, then Q. The right side is the converse of the statement, and we read it as Q, therefore P. As an example, suppose P equals Joe dropped the glass and Q equals the glass is broken. Then, we would read the statement as, if Joe dropped the glass, then the glass is broken. The converse would read, the glass is broken, therefore Joe dropped the glass. But, the converse is invalid, because the glass might have broken by some other means. Maybe someone else broke the glass, or maybe a baseball came through the window and broke it. The point is, there are many other reasons why the glass might be broken, so the converse is invalid. A fallacy similar to this is called the inverse error. The statement part, if P, then Q, is the same as before. But the inverse is, not P, therefore, not Q. Using our Joe dropped the glass example, the inverse becomes, Joe did not drop the glass, therefore, the glass is not broken. However, we know that there are many other reasons why the glass might be broken, even if Joe did not drop it. So, we cannot conclude, just because Joe didn't drop it, that the glass is not broken. Therefore, the inverse is invalid. Our third fallacy is improper induction. This means drawing a conclusion based on a few examples. For example, consider the following function. If we set x equal to 1, the function will equal 1. If we set x equal to 2, the function will equal 2, and if we set x equal to 3, the function will equal 3. Using induction, we might conclude that the function will equal whatever value we set for x. However, if we set x equal to 4, we find that the function does not equal 4. It equals 10. Induction has led us to a false conclusion. The fourth fallacy on our list is called begging the question. This is a term that is often misused because it does not mean begging for the question to be asked. Instead, it means circular reasoning. This occurs when the thing we're trying to prove is used as part of the proof that the thing is true. For example, we could argue that Joe's favorite color is red because Joe drives a red car. But this argument assumes that the color of Joe's car is his favorite color, in order to prove that the color of Joe's car is his favorite color. That is circular reasoning, or begging the question. Fallacy number 5 is appeal to authority. In science, a proclamation by authority or a consensus of opinion by individuals is not a valid basis for conclusion. The truth does not depend on popularity or who says it. You can find many examples throughout history, and even today, where the highest authorities have believed things which are not true. Our next fallacy, number 6, is called an appeal to ignorance. This assumes that a given theory is true if no alternative theory has been put forth or proven. Obviously, just because we don't have a better theory does not mean that the one we have is automatically correct. The seventh fallacy in our list is the straw man. This occurs when the original argument is replaced by a misrepresentation. Then, arguments are applied to the misrepresentation, but treated as if they apply to the original. To illustrate this, suppose that Joe's mom wants him to clean his room once a week. But since Joe didn't clean his room last week, his mom won't let him go out and play unless he cleans his room first. Joe says to his mother, that's not fair. None of my other friends have to clean their rooms every day. Why do I? But Joe is making a straw man argument because his mom is not asking him to clean his room every day, just once a week. So Joe is misrepresenting what he's being asked to do and arguing against the misrepresentation. Our next two fallacies are very closely related to each other. They are called the composition and division fallacies. The composition fallacy assumes that if something is true for a part, it is true for the whole. For example, Joe notices that if he leaves early for work, he will avoid most of the morning traffic. From this, Joe concludes that if everyone left early, then everyone would avoid the traffic. Meanwhile, the division fallacy is sort of the reverse of the composition fallacy. It asserts that, if something is true for the whole, it must be true for each part. For example, on a nice sunny day, a lake will look blue. The division fallacy would have us believe that each drop of water in the lake must therefore be blue. In case you didn't know, the lake looks blue because the surface of the water reflects the blue sky. Next, we have another pair of fallacies called the ad hoc and post hoc fallacies. Without evidence, the ad hoc fallacy assumes that any series of possibilities are true. This allows one to conclude anything you can imagine. For example, suppose that Joe is late for a meeting. Maybe he got up late and was in a hurry and probably driving too fast. If so, he could have missed a turn on Switchback Road and drove over the cliff. Therefore, our ad hoc theory suggests we should call the hospitals or the morgue. However, we have no evidence that any of the theory's assumptions are true. Meanwhile, the post hoc fallacy automatically assumes that anything that happens before an event must be the cause of anything that happens afterward. A common example of the post hoc fallacy is, since the rooster crows immediately before sunrise, the crowing must be what causes the sun to rise. I think we can all agree that's not valid. So that's our top 10 list of logical fallacies. However, there are also a few fallacies that are procedural instead of logical. Let's take a quick look at those before we're done. The first one is confirmation bias. This results from our natural tendency to see what we expect or want to see. Sometimes, when data doesn't fit our expectations, we might just discard it, while not realizing that we are actually altering our results. Other times, some data might be ambiguous. Again, there is a tendency to count it in the way that supports our expected result. When these types of biases are performed systematically, they can greatly influence the conclusions. Another common procedural fallacy is the ad hominem, which is also known as attacking the messenger. Essentially, ad hominems are insults. If an argument can't be defeated with facts or logic, an opponent may try to fight the argument by casting personal insults at the presenter, or at anyone who agrees with the opposing argument. Ad hominems are a diversion and do not address the facts or logic of the dispute. Our next procedural fallacy is intimidation. Like the ad hominem, intimidation does not address the facts or logic. Instead, physical or financial threats are made to try and frighten one side into silence. Finally, if threats aren't enough to silence the opposition, then outright censorship might be used to try to take away the ability for the opposing argument to be heard. Censorship is also commonly used to silence critics of an existing argument that is too weak to withstand any questioning. So, now that we are familiar with some common logical fallacies and the basic rules of science, we are ready to look at some present-day examples of scientific controversies. In our next video, we will do just that, by applying these principles to the theory of global warming and its dependence on human activity. I hope you enjoy these videos and will subscribe or share them with others.